Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and I'm here to work on free response questions for you. Today, we're going to work on question number 3 from the 2019 AP exam, which was one of the long free response questions. And as all the long questions are, it was scored out of 10 points. As you know, I always recommend that you work through the problems on your own before you listen to my explanation, and you really will need your calculator and a periodic table and your formula sheet to do that. I just want you to do well on this exam and to be able to show all your knowledge, and the best way to get there is to practice first. And then you can keep track of your score as you go through. So it's time. Let's jump right into the problem. All right, a student is given 50 mils of a solution of sodium carbonate of unknown concentration. To find the concentration of the solution gets mixed with excess 1 molar calcium nitrate, causing a precipitate to form. Here's the balanced equation. Okay, well, you can read that. I don't need to read that out loud to you. Part A asks, write the net ionic equation for this reaction. Okay, well, this is a skill all AP chemistry students should really be good at. So the key is to remember that your ionic compounds that are dissolved in solution need to be written as dissociated into ions. So if we look at the balanced equation, we're looking at sodium carbonate, right? It's in solution. So we've got 2 sodium ions with a +1 charge and a carbonate ion with a -2 charge. So we need to write that down. And then we've got the calcium nitrate solution. So we've got a calcium ion and 2 nitrate ions. Really pay attention when you're writing these that you've got the right number of ions and the appropriate charge indicated for these ions. One of the common mistakes I see with my own students is they'll not write the correct coefficient, or they'll make a mistake with the charge, or not write a charge in at all. And these are all errors that are going to cost you points, easy points that you should be able to do. On the product side, we have sodium nitrate in solution. So that's 2 sodium ions and 2 nitrate ions. And then the calcium carbonate, which is a precipitate, right? That's our solid. And so the precipitate needs to stay together as an undissociated compound. And so we have to write that into our formula as well. These are the steps you need to go through, all right? And then any species that are the same on both sides, you cross them out. Those are your spectator ions, and they need to go. And what's left is your net ionic equation. And if you want to rewrite it because you just like to write things extra times, here you go. This is what you would end up writing. It's not necessary to rewrite it, but I did. Just another tip, if you're very good at this, you can actually work backwards from the precipitate and then write that as your product and write the ions that form the precipitate as the reactants. That can be a quicker way to go. But I thought I should be more thorough. All right, so that's part A. It was 1 point, all or nothing. Everything was right or it wasn't. That was all there was to earn that point. But in terms of AP chemistry skills, this is something you should absolutely be able to do. All right, the diagram below is incomplete. Draw on the species needed to accurately represent the major ionic species remaining in the solution after the reaction's done. Okay, so it shows calcium carbonate on the bottom. Although the arrow gets cut off, that's okay. And then we've got sodium ions in solution and nitrate ions in solution. Well, what's missing? All right, the key is that you're told there's excess calcium nitrate added to the sodium carbonate, which means I've got extra calcium ions and extra nitrate ions floating around. All right, I already know from the balanced equation, if everything reacted in the exact stoichiometric ratios, that I should have 2 sodium ions and 2 nitrate ions. But if I look at the beaker, there are 2 sodium ions and there are 4 nitrate ions. All right, and so there must have been 1 calcium nitrate formula unit that reacted. There's 1 excess calcium ion in the solution, and that's what I need to put in. All right, and if you put in 1 calcium ion, you got the point. If you drew in something else, if you put in more than 1 calcium ion, you did not get the point. So it was very particular here. All right, but easy enough to work out, very doable. All right, part C. All right, the student filters and dries the precipitate of calcium carbonate. They actually told you what the precipitate was in the problem. They give you the molar mass of calcium carbonate, and here's our data. We had 50 mils of sodium carbonate solution. We added 100 mils of calcium nitrate solution, and we calculated collected 0.93 grams of the precipitate. And so the question says, well, how many moles of sodium carbonate were in that original 50 mils of solution? So it's a stoichiometry problem, all right? And we did have the balanced equation. So from the mass of the calcium carbonate, I can calculate the moles of calcium carbonate. They even gave us the molar mass, right? So they made that very easy. All right, so we can calculate the moles of calcium carbonate. I should only have 2 sig figs there, and I wrote down 3, but that's okay. And then from the balanced equation, I see that the moles of calcium carbonate and the moles of sodium carbonate, they both have a coefficient of 1. All right, so for every mole of calcium carbonate that I formed, I had 1 mole of sodium carbonate reacting, and therefore the answers are the same. If you're being careful about sig figs, you probably should have written down 0.0093 moles, but we're okay. All right, and this again was 1 point. Either you got the right answer and you had reasoning to back it up, or you did not. All right, let's go on. The student realizes that the precipitate was not completely dried and claims that as a result, the calculated sodium carbonate molarity is too low. Do you agree with the student's claim? Justify your answer. Right? The College Board loves these kinds of questions for the AP Chemistry exam. Here's a claim, agree or disagree, back it up. Okay, well, we can do this, all right? So let's think through the reasoning here, all right? The precipitate was not dry, and therefore it must have contained water, all right? So the mass of the precipitate is really larger than it should be for the actual amount of calcium carbonate formed. My 0.93 grams here is actually too big a number, and if it had been completely dried, I would have had a lower value. Well, here's what that's going to do to my data, all right? We know that the moles of calcium carbonate gives me the moles of sodium carbonate. So if my mass of precipitate is too big because of the excess water, I'm going to get a too large value for moles of calcium carbonate when I do my math, like I did in part C. And that means when I go to calculate my moles of sodium carbonate, that's also going to be too big, all right? So when I think about the molarity, molarity is moles over liter. So it's moles of sodium carbonate over the volume of the solution. My numerator is now too big, all right, because I had a erroneously large mass of precipitate, which means my calculated sodium carbonate molarity would be too big. So I disagree with the student's claim, and I've got my justification. This again was also 1 point, but you had to work through it and you had to show the logic of how you did it. You don't have to write a lot, but you do need to back up your answer with math-based reasoning. That's what they mean when they say justify your answer. Okay. Let's go on to part E. After the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it conducts electricity. What would you observe? Justify your answer. Okay, so this solution would conduct electricity. How do we know that? Well, let's go back and think about that particle level model we filled in a couple of parts back. We've got ions in solution, and these ions are free to move. We've got sodium ions, we've got nitrate ions, we've got excess calcium ions. All right, there are mobile ions in solution. We can even go back and look at our the products of our complete ionic equation, and we see that there are mobile ions in solution, and therefore, yes, it will conduct electricity. So that was a 1 point question. I don't believe you had to state what ions were present in solution. Of course, you could do that, but that wasn't strictly required, I think. All right. And then the question continues. The student decides to find the molarity of that sodium carbonate solution using a different method. All right, and all of a sudden it turns into an acid-base problem, equilibrium. Okay, but we can do this. We're not going to be flustered by that change. All right, so F part 1. The student first decides to find the concentration of hydroxide in solution, and then use that to find the initial concentration of the carbonate. So F part 1 says, identify a laboratory method that's not titration that the student could use to collect the data to find the hydroxide ion concentration in solution. Well, what if we did pH? We could get out a pH meter and take the pH of the solution, right? And that would work, and you would get your point, all right? You did need to be a little more detailed here, that really a pH meter is your best choice here, all right? And it was 1 point, all or nothing. Either you got it or you didn't. But then it continues. There's a second part to part F. All right. How could the student use this measured value to find the initial concentration of carbonate ion? They didn't want you to do the math here. They want you to explain how to get their answer. And there's kind of a lot to do here. Okay, so here's what I did. All right, we measured the pH with the pH meter, but I want hydroxide ion concentrations, but I know that pH plus pOH add up to 14, so I can find the pOH, right, by subtracting the pH from 14, and then I know 10 to the negative pOH will give me the hydroxide ion concentration. Okay, that's the first thing I needed to do. And then I need to think about it from an equilibrium perspective, all right? We can make the assumption that the hydrogen carbonate ion concentration is equal to the hydroxide ion concentration because they're in a 1-to-1 ratio and there's no other significant source of either of these ions in water, all right? So then we can start thinking about it from the Kb expression, all right? If I know that those two concentrations are equal and I have that number, I could then substitute all that into my Kb expression and solve for the equilibrium concentration of carbonate, right? So mathematically, that's fairly easy to do. We can also think about this from an ice table perspective, all right? I don't know the initial concentration of the carbonate ion, the hydrogen carbonate ions and the hydroxide ion concentrations, so we're assuming starting at 0. The system has to proceed in the forward direction to establish equilibrium. But from the pH, right, and what I just talked about, we can actually calculate the equilibrium concentrations of hydrogen carbonate and hydroxide ion. And then from the Kb expression, we can find the equilibrium concentration of carbonate. So that would fill in that last bit of the table. And we have X because that's what 10 to the negative pOH gives us. So finally, from our ice table, we can find the initial concentration of the carbonate from taking the equilibrium concentration of the carbonate and adding in the hydroxide ion concentration. Whew. You know, quite frankly, I almost think it would have been easier just to do the math and just to do the calculations, but that's not what we were asked to do here. All right, so there were 2 points available for this problem. One point was for figuring out how to get the hydroxide ion concentration, and then the second point was finding an accurate way, right, a realistic way to get to the initial concentration of the carbonate ion, right? And so that's what you needed to do here. I think that second point was hard to earn for a lot of students. All right, in the original sodium carbonate solution at equilibrium, is the concentration of hydrogen carbonate ion greater than, less than, or equal to the concentration of carbonate? Justify your answer. All right, remember, justify your answer always means use math-based reasoning. Okay, so for this, what we really need to look at is the Kb value, all right, for this balanced equation. The equilibrium constant is less than 1. When an equilibrium constant is less than 1, that means that reactants are favored, all right? And so if I've got more reactants than products, I'm going to have more carbonate than hydrogen carbonate ion, all right? And so that's really what you needed to say here. This was also a 1-point question. So you had to have reasoning. You really needed to refer back to the Kb value and come to the realization that the hydrogen carbonate ion concentration is less than the carbonate ion concentration. Okay, but wait, we're not done yet. There's always more, right? These problems go on and on. The student needs to make a buffer with carbonate and hydrogen carbonate, all right? Would this be an appropriate solution to use to make a buffer with a pH of 6, all right? All right, okay. So let's think about this, buffers. Always one of the hardest topics in AP Chem for all students. So buffers, when you're thinking about making a buffer, what you need to think about is that they're most effective within 1 pH unit of the pKa of the weak acid. Now what we have here is a Kb for the weak base carbonate. Okay, so we're going to have to do a little math. Let's get a pKa value for hydrogen carbonate, which would be our weak acid here. All right, we know that Ka times Kb equals Kw, 1 times 10 to the minus 14th for a conjugate acid-base pair. That formula is conveniently on your formula sheet. Woohoo. All right, so we know Kb, so we can calculate Ka for the weak acid, which would be hydrogen carbonate. And we get 4.8 times 10 to the negative 11. Okay, to find the pKa, we need to take the negative log of the Ka, and we get a value of 10.32. All right. Well, if we want a buffer with a pH of 6 and the pKa is 10, All right, that's more than 1 pH unit away. All right, so this would not be an appropriate choice to make a buffer with a pH of 6. We've got our reasoning, all right, we backed it up, and we can talk about why this works. All right, if you want to make a buffer with carbonate and hydrogen carbonate, you're really going to be most effective in the pH of 9 to 11 range, not 6. All right, so wow, this was a long problem. It was a good problem, but not an easy problem. It was 1 point for all of that. Okay, how did you do? The average score in this question in 2019 was really 3 points out of 10. I would say out of the 10 points, 4 or 5 of them were fairly easy, but not for everybody. And several of them, 2 or 3 of the points were really quite difficult to get. So if you got 3 points, you're fine. If you got 4 or 5 points, you're doing well. If you got more than that, then I'm really impressed. If you haven't subscribed to my channel, I'd really appreciate that. Have a good day.